Okay, so yeah, so in this, I changed slightly the title of the talk, but I'm going to talk about black holes. And I should also apologize to those who closely follow the story, because in these 30 minutes it will be mostly introduction. So I wouldn't be able to say much details about the new things, but the claims are written there. So those who are following the story can read, see the claims, and then I'll be very happy to discuss it with them in details afterward. Okay, so let me just start from the general motivation and introduction. The general motivation is that we want to understand how generic inflation is. If we start from inhomogeneous initial data and we assume that we have an inflationary potential which is sufficiently flat so that we can approximate the inflationary potential with the CC. So the problem is, this is a simplified problem. I approximate the inflationary potential with the dead CC, and I'm asking, given some generic initial data, what will be the final state of the universe? Okay, so, and the general theme is that the topology of the universe is going to constrain the final state. So to motivate this, or to just convince you that this is a natural expectation, is let me just start from the simplest possible example. Just consider FRW cosmology with positive lambda, and let me write the Friedmann equation. So we have positive rho. In fact, we have a positive contribution to rho from the cosmological constant. And here we see that if kappa is equal to 0 or -1, which corresponds to flat or open universe, then we inevitably get the zeta as the final state. If kappa is positive, which means that if we have a closed universe, then there are two possibilities. Either we satisfy this total energy momentum tensor satisfies a strong energy condition, or we satisfy, if we have, if the Einstein equations are satisfied, the time-like convergence condition are satisfied. In that case, we recollapse. So, or let's call it big crunch. If we satisfy time-like convergence condition, otherwise we get the zeta. Okay, so what we see here is that in this simple case, there is actually a connection between the topology and the final state of the universe. If I fix the topology, which is a discrete choice, at my initial on my initial Cauchy slice, in some cases I have no choice but to get the zeta. So one can continue to make the problem more generic by, for instance, relaxing the assumption of isotropy, keeping homogeneity. So then we are dealing with Bianchi universes and S1 cross S2, and this is something that Wallace studied. And he reached the same conclusion that in all topologies, or in all Bianchi universes except Bianchi type 9, so anything except this, will go to the zeta with the characteristic time scale that is of order of 1 over square root of g lambda. So what we expect from the zeta with that value of CC. So again, the connection, and this Bianchi type 9 is basically the one that contains S3, a closed universe, as a subclass. is the same topology that in the for W case allows for a global recollapse. Okay, so these are the simple cases, the homogeneous cases. Of course, when we relax the assumption of homogeneity, the problem becomes much more complicated. For instance, we can form black holes, so there is no hope, or there is no sense in which it becomes exact de Sitter in the asymptotics. However, one would, for instance, want to find, for instance, in the case of inflation, we would like to say something like there exists some patch that expands like de Sitter. So there will be some inflationary patch. So let's consider inhomogeneous cosmology. I don't write cosmology. So can we say something interesting in this case, given that the problem is much more complicated? And it turns out that, yes, we can make some interesting statements, again, relating the topology to the final state of the universe. And this interesting statement was made by Barrow and Tipler, and then it was rediscovered after more than 30 years by Leonardo and Matt Kleban. However, I think a lot of credit should go to Leonardo and Matt Kleban, because they rediscovered it from a much more modern perspective. So while in the past they were more interested in asking what are the situations in which they were trying to show the genericity of global recollapse, because it was written before discovery of lambda. So they're basically asking a different question. Here now our focus is the possibility of not having a global recollapse, as I named the talk. So we want to see whether we have surviving regions that would inflate. So what are these theorems? So there is, what should I call it? Global recollapse theorem. So what is the statement? The statement is that let's start from a compact. Let's work with a spatially compact cosmology. It can still have many different interesting varieties of topology. So start from a compact cosmology. This is supposed to be some space-time diagram, a Penrose diagram. And we, let's see, so we have some initial slice, sigma 0. Now I should draw it over here. So there is some initial slice, sigma 0, with the condition that k is positive everywhere. Oh, and k is the expansion rate. So it's everywhere expanding at the initial time. And let's assume that this cosmology has a global recollapse. So it has a singularity. And let's also assume that this singularity is a crossing singularity. So what is a crossing singularity? A crossing singularity is a singularity similar to what we have in the singularity of Schwarzschild black hole. The definition is that there exists some time function, some set of Cauchy slices near this singularity, such that the expansion, the extrinsic curvature, the trace of extrinsic curvature of those slices asymptote to minus infinity, if we are talking about the future singularity. In the case of past singularity, it will be the opposite. This is the situation for the singularity of Schwarzschild black hole. It is also the situation when we have, for instance, some Cauchy horizon, like in the exact Kerr geometry, or Reisner-Nordstrom black hole, there is a Cauchy horizon. Near that Cauchy horizon, again, the same condition is satisfied. So it doesn't really, well, even though we believe that those are fine-tuned situations, again, they satisfy this criteria. Anyway, so this is, assume that there is a crossing singularity here, which means that k goes to minus infinity. There are slices that on which k goes to minus infinity near here. Now these two conditions, slices with k going to minus infinity and an initial slice with k larger than 0 everywhere, these two result in the existence of some maximal slice with k equal to 0 everywhere. So this is called sigma maxima, where k is equal to 0 everywhere. Let me just give you some simple example. This is the analog of the fact that if you have a continuous function that between 0 and 1, it goes from some positive value to a negative value, it crosses 0. It's some generalization of that. It's not as trivial to prove it, but it is true. OK, so we have a maximal slice. If we start from expansion and go to the global Ricolas, now what do Barrow and Tipler and Leonardo and Matt do? They look at the 0,0 component, or the Hamiltonian constraints of GR. So if I take the Einstein equation and contract it with the normal to the Cauchy slices, and I use the Gauss-Kodazzi equation to relate the curvature quantities, to rewrite them in terms of intrinsic and extrinsic curvatures of the slices. Then I will get some equation that relate the extrinsic curvature of the trace of the extrinsic curvature of my Cauchy slice to some other quantities. So what are those other quantities? There will be 16 pi g times lambda plus T mu nu matter and mu and nu plus sigma mu nu squared. This is the anisotropic expansion, so the traceless part of k mu, k mu nu, the traceless part of the extrinsic curvature of my slice, minus the intrinsic curvature of the slice, R3. So this will be, I will get this equation. Now let's apply this equation to this slice. So it has to hold everywhere, including on this maximal slice. On the maximal slice, so on sigma maximum, k is equal to 0, so the left-hand side is equal to 0. Here lambda is positive, T mu nu times n mu, and nu is positive by the assumption of big energy condition, which is a special form of dominant energy condition. So this is positive, this is non-negative, this is non-negative. So what it tells me is that in order to have this sigma maximum, I should have R3 larger than 0 everywhere. And then they use the result from the topology of 3D manifolds. Which says that there is only a subclass of manifolds, 3D manifolds, that can accept everywhere positive scalar curvature. And that subclass can be written as, so the only possibility for this to happen is that this sigma maxima is equal to S3. Basically, the statement is that it would be either spherical or S1 cross S2, like a cylinder, or a connected sum of this. Connected sum is basically one way of gluing different manifolds. And then there will be more generalization by some identification of this with some symmetry group. So this is the most general thing that one can write. And a number of S1 times S2. So only in such situation we can have a global recollapse. And these are the manifolds that are essentially the generalization of the closed cosmologies that we had here. By the way, it should be, this comparison has to be made, right? This equation is just the generalization of this equation. And that R3 there is the generalization of this kappa here. So that's why the ones which which accept positive R3 everywhere, we can call them closed cosmologies. They correspond to kappa being 1 here. And then H and this K are related by a factor of 3. So this is, I'm just generalizing that here. All right, so this is the global recollapse theorem, or maybe better to call it a global non-recollapse theorem. If you have an open or flat sigma, then there will be no global recollapse. And open and flat means everything except this. Of course, they have more specific definition in terms of the basic elements.
These have a very rich topology, like negatively curved spaces. Do you put any condition that the shortest cycle be bigger than something?
No.
Okay. I mean, because there are interesting UV effects that happen when the cycles are small, including topology change that reduces it down to the previous cases. That's, of course, an extra input from.
No, well, we are working. We are working in the. So yeah, maybe I should have mentioned. This is purely classical GR. So, and I am talking about. In fact, maybe I should have mentioned this. So we are working within the domain of hyperbolicity of my initial Cauchy slice. Either this manifold is globally hyperbolic, or if it's not, I'm just restricting to that domain, which means that every slice has the same topology, the same 3D topology as the initial Cauchy slice. Right.
The most important part is to say that there are some part which continue expanding.
I am not objecting to it, but I just think it's an interesting.
There could be some part which is small.
I'm saying the way that goes is if it's small, maybe it doesn't get small, but Casimir energies can make it shrink a bit. If it's small and it undergoes topology change, it can revert to the upper cases. You lose the
Mm-hmm. Yeah, although, yeah, I guess.
Really important here, but it's probably something to put in the specification.
Yes. Yeah, I guess that is inside the specification. That I am in the domain of global hyperbolicity, and there it doesn't change. The topology doesn't change.
I'm just saying whenever it gets UV sensitive, you have to worry about it.
Yeah, that is what I call singularity in this case.
I guess here what you're talking about probably is that what he says, the part of the universe continue expanding. For the part of the universe that continue expanding, whatever you say is not applicable. But there is a part of the universe which may start collapsing. So this is what you say.
No, I'm saying something. It's not. I didn't mean for this to take over. I'm saying that you could have topology change that reverts the open case down to the.
Okay. Yeah, I'm saying I cannot within this assumption. All right. So yeah. So okay. Well, now we want to go beyond that, of course. And one thing that we can, I should add, and I think Leonard and Matt already added, is that we can say something about the open and flat cases. So this was some global considerations about this manifold. Now, if I want to say something more, it seems that it's inevitable to find some choice of time slices. So we are talking about inhomogeneous space-time. The choice of, there's no special symmetry. The choice of time slicing seems kind of arbitrary. However, there is some choice of time slicing which seems to be the perfect choice for this problem, and that is called the mean curvature flow. So what is the idea? In general, I start from the initial Cauchy slice, and then imagine I'm just doing solving Einstein equations numerically. I have to choose the lapse function and a step forward. So I should produce the later Cauchy slices. So the question is, how do I choose this lapse function? And there is a very useful choice for this lapse function, which is to take it to be the volume maximizing choice, which is called mean curvature flow. So mean curvature is this K. That is called mean curvature because it's the trace of the extrinsic curvature. And mean curvature flow is to choose the lapse function to be this mean curvature. The lambda is the parameter of the flow, and I choose it to be K. And this is, and if you remember, this K is basically the derivative of the volume element, or the logarithm of the volume element of our Cauchy slice. So this is really taking longer steps where the volume is expanding faster and shorter steps when it's expanding slower. One can show that, well, basically it's almost obvious. This, if I start from everywhere expanding initial slice, this is a choice of a legitimate choice of lapse parameter because it's everywhere positive, so it moves me forward. Moreover, this stops only if I reach the maximal slice when K is equal to 0. And well, in this geometry, it does not stop, well, unless it hits a singularity. However, one can show that with this definition of singularities, if I assume that my singularities are all Crossing, then this mean curvature flow will not approach the Crossing singularity. So what does it imply? It implies that on open and flat, especially open and flat geometries, this mean curvature flow will never stop. And then by looking at this equation, what we see is that there has to exist a point on every slice of this mean curvature flow such that K at x is larger than or equal square root of 24 pi g times lambda. Exactly because there has to be a point with R3 less than or equal to 0. They cannot, in this manifold, I cannot have R3 positive everywhere. Okay, so these are the known facts so far. Very interesting. Now, there are some questions. We want to, how much time do I have? -5, 7 minutes, okay. So let me just say what are the questions and what, is it visible, more or less? Questions. So of course we want to generalize, make a stronger statements. One is that one interesting thing to do is to relax this assumption about the initial condition. So one is the initial condition. Why do I want to relax it? I'm basically get inspired by the Penrose singularity theorem. Penrose just requires the existence of an anti-trapped surface to tell me that there is an initial singularity. So the question is that can I reduce the assumption about the whole Cauchy slice to something more minimal, like a surface? Can I prove that if there is an anti-trapped surface, I will get, I won't have a future singularity, so a non-singularity theorem based on the existence of an anti-trapped surface with particular topology. So here I'm talking about these surfaces which are somewhat topologically non-trivial. Like for instance, if I have a toroidal universe, this is an example of a flat manifold. This is one of those manifolds that cannot have positive Ricci scalar everywhere. And this kind of manifolds can be shown that they all contain topologically non-trivial surfaces, like this T2 surface that I have shown in here, with genus 1 or larger. Genus is the number of hosts. So, so they are non-spherical. So all of these manifolds contain those kind of surfaces. And one can imagine the following situation, and that's one of the claims here. If I have a surface on my initial slice that is everywhere which is anti-trapped, which means that if I consider its light cone is expanding in both directions, then it's expanding in both directions everywhere, then Penrose singularity theorem will tell us that there will be a singularity in the past. One can combine that assumption with the assumption of crossing singularities. So the fact that there is a singularity in the past, and the fact that if the singularity is crossing, then I should have slices which are everywhere expanding. So therefore, k goes to positive infinity. I can combine these two assumptions to basically get rid of this assumption about the initial Cauchy slice. So the initial Cauchy slice doesn't have to be expanding everywhere. The existence of anti-trapped surface guarantees the existence of Big Bang singularity. The existence of Big Bang singularity plus the assumption of crossing singularities guarantees that I have to have these slices with k positive everywhere, and then the rest of the argument follows. So that is some kind of generalization that one can make. The other thing is that can one say something about the topology of the singularities that can appear in these geometries? So black holes, or topology of black holes. And again, the answer is yes. One can say something about the topology of black holes, again, based on these surfaces. So what can we say? We can consider, as I said, these topologies, this spatial topology will always contain surfaces with genus larger than or equal 1, which are topologically non-trivial. So one can consider one of them, say something in between, which is a minimal surface, and then try to repeat the arguments that I gave over this minimal surface. So what can I say for a minimal surface? I can write R3 on that minimal surface, or on any surface, as R2 minus the extrinsic curvature of that, plus h squared, the trace of extrinsic curvature of that surface, minus twice h prime. So if it is minimal, then h is equal to 0 and h prime is positive. And that implies that if the genus of the surface is larger than or equal to 1, then the integral of R3 over this surface is going to be, let's see, so this is 0, this is positive, sorry, 0, negative, 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 or non-positive. So this will be, or actually everything non-positive. So this will be less than or equal to 0. So if I just put this condition inside one of this equation and do some massaging, one can get the following equation, that the area of these minimal surfaces, this incompressible non-spherical minimal surface, has to expand at least exponentially. So d log s d lambda has to be larger than equal 8 pi g lambda. Now this immediately restricts the topology of black holes, because it tells me that they cannot contain surfaces with this topology. So I guess there are other questions. For instance, one can ask, well, can we show that there is an observer who feels being in the center? Given the structure of singularities, I think one can make statements like that, but I guess we should leave it for future.